Universe. 200 billion galaxies grouped into clusters. Each galaxy consists of an average of 200 billion stars. Most stars have planets revolving around them, on one of which life emerged consisting of molecules and atoms. According to modern science, everything in the universe consists of a limited set of particles. These particles are elementary, that is, they themselves do not consist of anything. All known particles are listed in this table. Particles here are ordered by mass, electrical charge, spin, and participation in fundamental interactions. Fermions have half-integer spin. Bosons have a whole spin. Fermions are distributed among generations. Each subsequent generation has greater mass. Finally, fermions are divided into quarks and leptons. One of the differences between quarks and leptons is that quarks participate in the strong interaction, the carrier of which is the gluon. Quarks and electrically charged leptons participate in electromagnetic interaction, the carrier of which is the photon. And finally, all elementary particles participate in the weak interaction, the carriers of which are the W and Z bosons. In addition, particles with an electrical charge different from zero also have antiparticles, which do not differ in anything other than their charge from ordinary particles. When a particle interacts with its antiparticle, they annihilate, emitting 2 or 3 photons. Mass is an indicator of the inertia of a body. That is, the greater the mass of the body, the more energy is required to put it in motion. The electric charge determines the ability of a particle to be a source of electromagnetic fields, and also makes it possible to take part in electromagnetic interaction. Spin shows how much the particle needs to be rotated in order for it to take its original position. Quarks have half-integer spin and participate in all 3 types of fundamental interactions. They do not occur in a free state, but are always found in hadrons. Hadrons are divided into 2 types, mesons and baryons. Mesons consist of 2 quarks, baryons, of 3. The nucleons that make up the atoms of the matter around us are classified as baryons. Leptons, like quarks, have half-integer spin. They participate in weak interactions, and those having an electrical charge different from zero also participate in electromagnetic and strong interactions. All 3 types of neutrinos participate only in the weak force, which operates over extremely short distances, so they can travel vast distances without interacting with anything, and have enormous penetrating power. Nucleons and electrons form atoms, which make up almost all visible matter in the universe. The next group of elementary particles are gauge bosons. They are carriers of all known fundamental interactions. W and Z bosons mediate weak interactions. It allows elementary particles to transform into each other. W bosons give particles the ability to exchange mass, charge and spin, and Z bosons give them spin and momentum. W and Z bosons are very massive. Their mass is comparable to the mass of cesium atom. Their exceptional massiveness determines the very short distance over which the weak interaction operates. The characteristic range is 1/1000th the size of a proton. The weak interaction is also responsible for the beta decay of atomic nuclei. Another type of gauge boson is the photon. It is responsible for electromagnetic interaction. Only particles that have a positive or negative electrical charge participate in it. Another property of it is its infinite range, since the photon is a massless particle. Electromagnetic interaction is responsible for many processes in the micro and macroscopic world. Attraction of bodies with charges of different signs and repulsion of bodies with the same ones. Elasticity, friction, surface tension, phase transitions, chemical transformations, electricity, light, magnetism, structure of atomic shells, length of chemical bonds. The photon is responsible for all this. The last type of gauge boson is the gluon. Quarks and hadrons consisting of quarks are susceptible to it. The strong interaction operates on scales on the order of the atomic nucleus. It holds quarks inside hadrons, as well as nucleons in atomic nuclei. A characteristic feature of the strong interaction is that with an increase in the amount of energy aimed at breaking the connection and accordingly an increase in the distance between the quarks, the intensity of this connection only increases. If the amount of energy is enough to break the connection, the quarks do not begin to exist separately, but a partner appears for each of the severed quarks. Thus there can't be free quarks. Currently, only one elementary particle belongs to the latter type, the Higgs boson. It is responsible for the mass of the W and Z bosons. Particles located in the Higgs field, receiving acceleration due to external influences, experience the resistance of this field, thereby acquiring inert mass. Everything in the universe consists of combinations of this relatively small number of particles. There are also many hypothetical particles. But, since their existence has not been proven experimentally, they are not included in the modern Standard Model.